Hello. In this question, we'll be looking at a first order differential equation, and you can see on screen, you can have a read yourself. It's a application question with a bar of soap, and we have time. We're given it before, so basically where t equals 0, and we have a volume, and we have 2 minutes later, so we'll be using that information. And of course, we're giving a rate of change, which is what we're dealing with here. So there's a technique involved called separating the variables. And what's basically done at A level is you will separate your variables, generally x and y, and you'll form integrals of both sides with respect to x, let's say. And then you integrate both sides, and from there might be a few different bits and pieces, depending on. So dy over dx, of course, is a derivative. In this case, we'll be using dv over dt with respect to time. So I'm just doing out the picture here, our little diagrams demonstrating the volume was originally 180 centimeters cubed, and of course with the reduction, so the change in the volume, we have 154 point, I have 3275, I'll just round it to 33 there, so 154.33 centimeters cubed. So dv over dt is equal to a negative kV. K is our constant of proportionality. Remember that dV over dt is negative. We're doing a reduction here. There's a reduction in volume. So we have dV over dt. We want to bring over our V. We want to put them together. So divide both sides by V, you get 1 over V. So our integration of 1 over V dV over dt times dt, which will cancel out the dt's, is equal to integrating our minus k dt. Natural logarithm ln v is equal to minus kt and plus c as our constant of integration. We have a decreasing exponential here, so as it gets closer and closer to 0, t gets larger, so as time goes on you'll see that. And we actually have a little bit of a interesting thing to happen towards the end here with this. So v is equal to e to the minus kt plus c, and we'll just plug in our a as well. A is, think of it as the initial condition, the initial value, which in this case we know is 180 centimeters cubed. This is the general solution for our differential equation, and now we'll look for a particular solution. So when t was equal to 0, we had our first diagram there. So we have AE to the 0 is equal to 180 centimeters cubed, so A is equal to 180. So from there I can actually plug that into now our second part. Let's say when t is equal to 2 seconds, 2 minutes, whatever it might be. You can change units with different questions and so on, but just keep it nice and simple now. We're looking for a particular solution here. So we're putting it together in some way like that to find k. So A was 180, as I said. And from there, just break it down. So divide by 180 on both sides. E to the 2, e to the minus 2 will become 1/2 ln. And so we'll just put it all together like that. And of course, your calculator does most of the work for you with that at the end. So it should be a small number. K is equal to 0.076. So you write our final statement there. So V is equal to 180 e to the minus 0.0769 t. You'll see it's a negative exponential, and as you increase t, this is a little thought experiment thing here, but if you increase t and kept going, like t is 10, t is 20, so as time runs on, it's decreasing, it's reducing here. And so what's happening? But actually, if you think about it, if you actually get your calculator out and do a few workings on it, you'll see that it actually never reaches 0. And so you could say that this being a mathematical model, which is what we're doing here, the soap never dissolves. And that's another interesting aspect just for something like this, an application of this.